Okay, so section 5.1 is really just about the history of the atom and the different parts of the atom. So about 2,500 years ago in ancient Greece, there were a couple of philosophers that were reasoning that if you keep cutting a piece of matter over and over and over until you get to the smallest part that you can't cut any further, that would be known as atomos, which is Greek for uncuttable, and this is Democritus who used the term. So this is where we got the word atom for the smallest particle of matter. And Aristotle later proposed that matter was made up of different components of the four basic elements, which at the time they called earth, air, fire, and water. This was embraced for about 2,000 years during the practice of alchemy. And alchemy was where they were trying to convert metals into gold. They were obviously not successful. However, there were some useful procedures that came out of it known as distillation. Distillation we talked about previously in chapter 2, and that's where we separate mixtures based upon boiling point or vapor pressures. Okay, if you take a look at the next page, this is where they talk about the first real scientists emerging. So in the later half of the 1600s, this is when Robert Boyle published his results from experiments, and he recorded them and wrote a book called The Skeptical Chemist. And this is how we came up with something called the scientific method. So he is the first person to actually publish his experiments with all of their data. And later on, there were other scientists, Carl Scheele, Joseph Priestley, Antoine Lavoisier, and Joseph Proust, that came up with some laws pertaining to what are substances made of and how do we follow the mass changes during chemical reactions. And then John Dalton, an English teacher, proposed a theory known as the atomic theory, and his points for the atomic theory are relatively important. Okay, so let's take a look at them. You're going to hear them refer to certain people's versions of the atom. So Dalton's concept of the atom was basically summarized in the atomic theory, which says that matter is made up of little tiny particles called atoms, and how we can't create atoms from nothing or just destroy them. Okay, this will fall apart in radioactivity, okay, where atoms that have unstable nuclei will spit out pieces of their nuclei to try and become stable. So that's how they form new atoms, okay, and then at the same time destroy them, okay. John Dalton also said that atoms of a certain element are identical to each other and different from other elements. Well, not all atoms of the same element are identical. This will fall apart when you talk about isotopes, which you should have talked about in biology briefly. Isotopes are atoms of the same element with different numbers of neutrons. And then John Dalton also said that atoms of different elements will combine in certain ratios to form compounds. And then during chemical reactions, the atoms will separate and rearrange, and then they'll recombine to form new compounds. Okay, you can pretty much bank on seeing some sort of a multiple choice question on a test pertaining to the atomic theory. Okay, now let's take a look at the bottom of the page. So now we're going to move on to using glass tubes to sort of probe matter to reveal what it's made of. So in the 1800s, a lot of scientists were really fascinated by matter and electric charge. And Julius Plucker in Germany and William Crookes decided to use these glass tubes to reveal the nature of the atom. So let's go to the next page. there's a lot of people in this section, okay? So it's always important that you know the person and what they're known for. So here we've got Crookes and his glass tube. So he had a sealed glass tube, and then he had a vacuum pump so that he could suck out the contents of the tube. And then he applied an electric sort of like charge to that tube. And what happened was, as he sucked out the air from that glass tube, while he had an electric charge applied at the same time, the air inside of it was glowing, and then eventually the glow faded as you removed all of the air. But he noticed that there was a shadow on the other end of a cross, because he had this metal cross placed inside of the tube. And there was a shadow. It was faint green at the opposite end. And then he also noticed that, something must have been traveling from one end to the other, because when you apply an electric charge, you're going to have a positive and a negative region. So something must have been traveling within that tube. And then what happened was, when John Baptiste Perrin put a magnet next to the tube, he noticed that the beam was actually deflected. When I say the beam, that means this sort of like green glowing substance, okay? So what this told us was that there must have been some charged particles being deflected by the magnetic field. And so he called this sort of like green substance a ray. They call them cathode rays, and cathode rays had to be made up of charged particles. Later on, we have an English physicist by the name of Joseph John Thomson, really famous guy. They refer to him as J.J. Thomson. He decided to modify Crookes's tube a little bit. And so if you take a look down here, what he did was, inside of the tube, he decided to put a positive and a negative plate. So here is my positive plate here and my negative plate here. And what he was trying to do was have those charged particles travel in between those two plates, because then he could determine whether they contained negative or positive charges. And here you can see that as it traveled in between the plates, they were actually deflected by the negative plate or attracted to the positive plate. So what this tells you is that this was made up of negative charges, because like charges repel and opposite charges attract, okay? He is actually credited with discovering the electron, okay? Okay. He calculated the charge to mass ratio of these particles, and he found that the value was 1.76 times 10 to the 8th coulomb per gram. And the mass of those particles was actually 2,000 less than a hydrogen ion. So he found the smallest known particle in the late 1800s. And if you take a look at the next page, he is credited with discovering the electron, and in 1906 he was awarded the Nobel Prize. Okay, now his version, J.J. Thomson's version of the atom, is also known as the plum pudding model. Okay, so Dalton's version of the atom has to do with his postulates from the previous page, but J.J. Thomson's model of the atom is here. And this is also known as the plum pudding model. You will sometimes hear this referred to as the spongy ball model. Basically, what he said was that the atom is this dense, heavy, positively charged sphere. So this whole red portion would be a positive sphere. And then dispersed throughout it, we have negative charges. The reason they call it plum pudding is because plum pudding is a vanilla pudding. That would be your positive dense sphere. It contains raisins in it, and the raisins would be the negatively charged electrons. Okay? Okay, now let's turn to the next page. J.J. Thomson had Ernest Rutherford working in his lab. So let's talk about Ernest Rutherford a little bit before I talk about Rutherford's famous gold foil experiment. So Ernest Rutherford won a scholarship to study at Cambridge with J.J. Thomson. And Rutherford fully believed in the plum pudding model. Rutherford left Thomson's lab to study at McGill in Canada. And while he was at McGill, what he did was he used samples of radioactive elements provided by Marie and Pierre Curie. Have you guys ever been to Paris and been to their coffins? Okay. And what happened was Rutherford worked with Frederick Soddy, and he used these radioactive elements to discover 3 types of radioactive emissions. So what this means is radioactive particles contain a nuclei that is unstable, so it spits out pieces of itself to become stable. The things that it spit out that he discovered were alpha particles, beta particles, and gamma rays. Okay? Alpha particles are actually a helium nuclei, so their particles actually are typically written like this. Okay, not really relevant to us, but I'm just letting you know. Beta particles are high energy electrons. Their symbols are typically written like this. Gamma rays, these are not matter, because matter occupies space and has mass. So alpha particles and beta particles are matter. Gamma rays will just go straight through you, okay? And the symbol for gamma rays typically looks something like this. Now, these different particles, or particles and rays, have different penetrating abilities and ionizing abilities. So alpha particles you could stop with a thin sheet of aluminum foil. Beta particles you can stop with a thin sheet of lead. Gamma rays, you're going to need some concrete, okay? Now, the reason why I'm telling you about this is because Rutherford used his knowledge of alpha particles to probe matter to reveal what it was made of. He wasn't setting out to disprove J.J. Thomson's plum pudding model, but he actually did. Okay, so on the next page, you're going to see a picture of Ernest Rutherford's gold foil experiment. This is a very famous experiment. He took a thin sheet of gold foil, which is obviously made of gold atoms, and what he did was he took a alpha particle source, and he shot alpha particles, which are positively charged particles, and he shot these alpha particles at the gold foil. He was expecting those alpha particles just to go straight through the gold foil and hit a detector on the other side. Okay, he wasn't expecting them to actually hit something really small that was positively charged in the gold foil, which means in the atom, and then be deflected. So sometimes these positively charged particles were deflected, and this is what led to the nucleus. Okay, so this whole experiment disproves J.J. Thomson's, I think I misspelled that. I don't think there's a P. So he disproved J.J. Thomson's plum pudding model of the atom, and this brings us to the nuclear model of the atom, which says that the atom contains a nucleus. So these alpha particles, here's my nucleus here. These alpha particles went straight through most of the time, but every once in a while, since alpha particles are positively charged, Once in a while, they hit that tiny nucleus, and since opposite charges repel, they went in a different direction. Okay?